Ferguson lead off. He's from Amarillo, and we also have Janice Maldonado on the author list, and Phil Schumacher will take the second part of the presentation. The talk will be effects of non-meteorological factors on severe thunderstorm warning performance. We're going to have Alex talk first and then have questions, and then Phil will take over and do the second part. If you have any questions, just raise your hand or put them in the question box. Go ahead, Alex.
Thank you, and good morning. Thanks for coming out. So yeah, like you said, our talk here is going to be effects of non-meteorological factors on severe thunderstorm warning performance. I'm taking suggestions on the title. Let me just put it that way. There's a couple of things which are actually a little bit meteorological here. I'm Alex Ferguson. I'm a forecaster at WFO Amarillo, and my co-authors are Janice Maldonado. She's a lead meteorologist at WFO Houston, and Phil Schumacher, the Sioux at WFO Sioux Falls. A quick introduction here to our topic. The motivation, it's pretty simple. First of all, severe thunderstorm warnings are a prominent National Weather Service product. When we issue those, the EAS system goes off. If you're watching local stations, you're going to see crawlers, inset maps, and they're going to sometimes break into your normal programming. Because of this, severe thunderstorm warnings may affect the actual and perceived false alarm rate. Over half of non-tornadic convective wind fatalities during 1986 to 2007 were unwarned. And that's squarely within the mission of severe thunderstorm warnings. Frustration as forecasters, that for me was the initial genesis for this. Lots of debate in the office based on two slightly different questions that have slightly different mindsets. Will it verify, or is it severe? And are our general assumptions accurate? So we came to this with assumptions just based on our experience doing warning operations. Our assumptions were that hail is easier than wind and that population greatly affects outcomes. General methodology, the study period for what I'm going to show you today is 2015 to 2021. We're going to be expanding this out, I think, to 2010 to 2021 since the switch to quarter hail. Sources, so your severe thunderstorm warning and severe weather statement polygons from the Iowa Environmental Mesonet. Events are from SPC Severe GIS. Population is at the block group level from the U.S. Census Bureau. Depending on year, it's both the 5-year American Community Survey or the decennial census. And these are adjusted using the National Land Cover Data Set, which is at a 30-meter resolution. A few different versions. You get a new version every few years of that. So the first thing is we want to estimate population density within each severe thunderstorm warning. We just used the initial severe thunderstorm warning for our population density figures. So we used a routine and ArcGIS for this. So starting down there on the bottom left, you see we've kind of got this purple hatching. Those are sort of your census block groups, and the red outline is our example severe thunderstorm warning polygon. So the first step is to reduce the coverage of the census block group polygons by essentially removing areas that are not in any of the developed classes in the land cover data set. So the developed classes are low, medium, and high intensity along with open area. I went ahead and kept those, but everything else, forest, open land, wetlands, forests, that all gets removed. And then we're going to clip the reduced block groups using the severe polygon. So you see we're reducing them in area and by what is and what is not developed, and then reducing by the severe thunderstorm warning polygon. Then we proportionally allocate. So a real basic example, if a severe thunderstorm warning polygon intersects 30% of a reduced block group that has 10 people in it, the severe thunderstorm warning is estimated to have 3 people residing in it. In practice, you're going to intersect several census blocks, and you'll take the proportion from each and then divide by the area of the severe thunderstorm warning polygon to come up with your estimated population density. Data processing, we're going to find the distance from the nearest radar. There's a quick and easy tool in ArcGIS for this. Use the centroid of the initial severe thunderstorm warning polygon and the starting location of a hail or wind event. Classify severe thunderstorm warnings and events. Use the programming language R for this, and the SP and RGDAL packages for some of the spatial aspects of this. We want to determine if the starting point of an event was within any severe thunderstorm warning or associated severe weather statement polygon in effect at the time of the starting point of the event. If so, the matched event was counted as warned. The matched warning was counted as verified. But if the warning had IBW tags, we required the relevant tag to be of severe magnitude. So if you had a hail event inside a severe thunderstorm warning that occurred at the same time and space, but the IBW tag was sub-severe, it doesn't get counted. And some final data processing. We bin our verification and event detection status by various attributes. That's going to be hour of day and UTC, climatological season, distance from the nearest radar in 40-kilometer increments. For events, we bin by phenomena as well. And for warnings, population density by deciles, that we use the densities of all counties across the continental United States to come up with those. We also did region, which in this case was climate region by NCEI. So here's a general review of those. There's also a series of abbreviations. You know, when I see those here in the upcoming plots, I'll try to read those out. So results, first taking a look at our seasonal, we see a pretty close cluster between winter, spring, summer, but fall tends to have a bit worse performance. Looking at POD, we see wind generally hanging below hail, except during the winter when they're about equal. This is one of the few times you're actually going to see the wind POD exceed the hail POD in really any. When we head to distance from radar, this followed our assumed pattern, but we can see with POD here on the right, it's really striking how much the performance falls off just for wind. In fact, most of this decrease in performance is due to poor wind detection at range. Makes sense considering beam height. You know, we can't see low enough for any wind information, but we can't see high enough to get a good idea about hail. So as kind of expected this a little bit stronger of a pattern than really sort of we were anticipating, but the pattern is the same. A year scattershot, little variation from year to year between 2015 and 2021. Hourly performance as expected. We have performance dipping at night, generally between 1 and 10 Z's when we see sort of the swoon in performance. And maximize performance, again, more reporters present. And, well, generally a more expected time for severe weather anyway, from about 8. Regional, so looking at some variations between regions. So, I mean, the big thing we had noticed that regional performance tends to increase as the aggregate number of events does. But, we do see some outliers here. So the Ohio Valley and the South, tend to have a little bit worse performance than you would expect just based on number of events. And Upper Midwest, Northeast, Northern and Regional Plains, and Southeast a little bit better. So why is that? Well, we got a couple of clues here, perhaps from the data. Ohio Valley and South, we look at the proportion of events here. Ohio Valley and South have a large number of wind events, and thus because of this, they likely end up with lower performance than expected based on the number of events alone. Of course, you may be looking at that plot and then explanation wondering, well, what's going on in the Northeast and Southeast? Well, we have higher background population density. So we look at the proportion of severe thunderstorm warnings within each of those density bins, and we see in the Northeast and the Southeast that there isn't this strong tendency for severe thunderstorm warnings to be in low population density warnings. Again, the densities are compared to the densities of all counties across the continental United States. States. A notable one would be the northern and regional, the northern Rockies and Plains. Strong performance despite higher proportion warnings in low population areas. This may be due to their higher number of hail events in the database. Could also be due to reporting biases. I suspect there's a lot of severe winds that may not be getting captured by our, by human reporters or observing systems. Another final note here, there's some noise here. I'll explain that here in a second. While the overall false alarm rate was highest for your lower population warnings, as we'd expect, some regions see this little relative increase in false alarm rate for high population warnings. This suggests that in some areas there may be defensive warning issuance occurring. Now, what I'm going to say first is those first two regions there, the Northwest and the Northern Rockies and Plains, for the Northwest, very few warnings in any of those bands. They just, did not have a lot. They don't issue a lot of severe thunderstorm warnings. So I'm kind of discounting that pattern there due to noise. In the Northern Rockies and Plains, there's only a very small handful of warnings in that top population bin. That may be causing their 100% false alarm rate there. But as we see in the upper Midwest, the South, in the Ohio Valley, we kind of see this little relative increase for higher population warnings. We don't see that overall, but overall in the CONUS, we sort of follow this expected pattern. But in some areas, you may be having defensive warning issuance. General conclusions here, our assumptions largely held. Like I said, our past experience as warning forecasters, but we hadn't seen a lot of quantification of this, at least for severe thunderstorm warnings. Better performance with more events, so using it as a proxy for total experience. Traditional severe weather seasons, so that's recent experience. The fall is in a lot of places. You don't think about the fall, or the fall is quite a ways away from any sort of seasonal training you've had. And that may explain the lower performance. Daytime hours, better performance, hail events, and higher population warnings. So pretty much tracks with the assumptions. And storms nearer to radar. One thing I would like to look at is sort of born out of frustration with using radar multiple requests. How do people do with their WFO's primary radar versus their secondary radar? So that's either their co-located radar, or like, for example, North Platte and Thedford, we would call Thedford their primary radar. I would like to take a look at that. And performance is going to be limited by observational capabilities. What we've all noticed, pretty intuitive, a striking decrease in detection of wind events at range due to beam height. Where could this help us? Training focus. So the first bullet point is, of course, way easier said than done with those observational capability problems. Wind events. So maybe try to focus a little more on wind events. Sometimes it could be. I mean, it's tough. It's tough without those observational capabilities. Quick refresher training if an out of season event may be ahead. I know down here we just had a real early season event before we even got going with seasonal training, and that might have helped shake off the cobwebs, so to speak. Human factors. Emphasis on traditional stats can sometimes lead to suboptimal decisions because you've kind of got the stats versus what a severe thunderstorm warning is. So the optimal question to ask is it severe? But as we kind of see out here in the data, because of sort of worrying about these traditional stats and maybe some of that increase in false alarm rate and higher population areas, you can see a little bit of evidence. In the back of your head, you've got a couple of questions that they're tough to suppress. Will it verify? Or for a high population area, will I get a stray severe report? And the final caveat, although we tried to examine, in some way we tried to examine this a little bit, all limitations of storm data are present. Various WFOs go to longer lengths to verify warnings, calling around, with plat books, rural phone directories the next day. Not every WFO does that, but some do. And so that can create some reporting biases. Alrighty, thanks everybody.